In a very general sense, when you take two similar ships, just one being larger than the other, you'll usually find that the bigger one is faster. For example, these 400-metre container ships typically have a speed of 25 knots, yet these feeder-style container ships might only have a typical speed of 15 knots. It's odd because it goes against common sense when you think that something bigger, weighing significantly more, will be faster. So, why are big ships faster than small ships? Well, firstly, we need to remember that a ship is just a hull displacing water. When you move a hull in the water, it generates waves which we see as the wash. At the bow, the waves are generated by the hull pushing water out of the way. At the stern, similar waves are generated as the water rushes to fill the void left as the hull moves forwards. From the side, it looks as if there's one wave system generated with its first peak at the bow, and a second wave system generated with its first trough at the stern. Now, it gets complicated fairly quickly if we have two wave systems, so let's just focus on the bow to begin with. At slow speed, you might get a wave profile like this. The wavelength is short and the wave speed is, well, it's the same as the ship's speed. As the ship speeds up, the whole thing stretches out, increasing the wavelength. This immediately tells us that the wavelength is proportional to the wave speed, which is directly linked to the speed of the ship. The higher the ship's speed, the higher the wave speed, and the longer the wavelength. As the ship's speed increases, you'll eventually get to a point where the wavelength is 2/3 of the ship's length. Your peaks are here and here, and your troughs are here and here. Remember though, we said that there are two wave systems generated, the second being at the stern, starting with a trough. The troughs from the stern system and the bow system are in the same place, so we get constructive interference. Behind the ship, a massive wash is generated as the bow waves and stern waves add together. While that doesn't help you on a ship, if you're on a small boat, pulling a wakeboarder for example, that might be what you need. Just find the speed that corresponds with a wavelength 2/3 of your boat's length, and you'll have the best water sports business in town. Anyway, back to ships. Let's see what happens as you further increase the speed. You'll get to a point where the wavelength is the same as your ship's length. Now, your stern wave and bow wave will destructively interfere, leaving minimal wash, but take a look at your hull. You have two peaks and only one trough. At this speed, the wetted surface of your hull and corresponding resistance are as high as they can be. This is known as your hull speed, which is the least efficient speed for a displacement vessel. You can approximate it using the formula speed in knots is equal to 1.34 times the square root of your waterline length in feet. For example, Queen Mary 2, with a length of 1,132 feet, has a hull speed of 45 knots. A 300-foot coaster will have a hull speed of 23 knots, an 80-foot small commercial boat will have a hull speed of 12 knots, and a 20-foot small pleasure boat will have a hull speed of only 6 knots. Of course, you can push past your hull speed. As you get faster though, your wavelength will continue to increase until you hit the point where it's 1.5 times your boat's length. Your boat's stern will sink, increasing your trim and creating the feeling of continuously running uphill, earning it the name hump speed. With the trough at the stern, again, you get constructive interference with the stern wave, generating a massive wash. This really is the worst speed to run at, but once you get over the hump, there is the potential to reach really high speeds. This is known as planing, where the wavelength can be many times your own boat's length. The thing is, a displacement hull like you find on most cargo ships will never be able to generate enough energy to get past its hump speed, so they can never plane. You can only reach a plane with a hull designed for it. Small speedboats, ribs and things like that. Anyway, combining all of today's examples together, we can produce a nice little graph with the hull's resistance, caused by the wave pattern, at different speeds. Notice how it's not a nice smooth curve. There are humps and bumps causing little sweet spots at different speeds. As the length of the ship increases, the speed at which all these humps and bumps occur changes. Longer ships experience sweet spots at higher speeds, meaning bigger ships can be naturally faster than smaller ships. But, of course, that isn't the whole story. You can reduce resistance from the bow wave using a bulbous bow. It generates a second bow wave designed to destructively interfere with the first, reducing all the effects that we've just covered. Alternatively, you can adapt the shape of your hull to reduce the waves generated. Finer lines like a long thin hull with a sharper bow will need to push the water far more gently, reducing resistance and helping the ship to get over its hump speed. This is how things like this 300-foot ferry can travel at 40 knots, despite having a hull speed of only 23 knots. Of course, if you're not limited by power, you can always just strap on a massive engine and not worry about the effects of resistance and go at whatever speed you like. Unfortunately though, particularly in the commercial world, that just isn't an option, which conveniently brings us back to our original question. Why are big ships faster than small ships? Well, they're not necessarily, but it is, in a way, easier for bigger ships to travel faster, as they experience prohibitively high drag at higher speeds, due to their greater waterline length, giving them a naturally higher hull speed.